Hello everyone, I'm Koiman from UC Riverside. Today I'm excited to bring you the strong revival of the classic DNS cache poisoning attack by leveraging a network side channel we discovered. This is the joint work between UC Riverside and Tsinghua University. Here's the outline of today's talk. Let's start by talking about the DNS cache poisoning attack first. The idea behind the DNS cache poisoning attack is to poison the cache of a DNS resolver, so that the traffic to a domain will be hijacked to a malicious host. The attacker can therefore use it to conduct cybercrime like scamming. Let's go through it step by step. To begin with, we have a victim resolver, a name server, and an attacker Trudy. We assume Trudy is the legitimate user of the resolver and cannot sniff or modify the traffic between servers. Usually, the resolver will cache the mappings between the domain name and the IP address after it receives a response from the name server. Based on this, Trudy first sends a query to the resolver to trigger an outgoing query on it. As expected, the resolver queries the name server. However, Trudy then injects a packet to the resolver by spoofing the identity of the name server right before it responds to the query. The resolver then accepts and caches the fake response. Now the authentic response arrives, but it's too late and dropped by the resolver. Since the resolver has cached the fake response, all future queries will be responded with the wrong answer. Let's move into Trudy's view. So how to craft a valid fake DNS injection packet? From the packet disassembly, we can see there are two unknown fields. UDP destination port, which is the same as the ephemeral port number, and transaction ID. Both of them are randomly selected by the operating system of the victim resolver. This requires the attacker to guess both values in a short time before the resolver gets the legitimate answer, which is quite challenging and has remained impossible since 2008, when Dan Kaminsky popularized the traditional DNS cache poisoning attack. Surprisingly, we made this possible again by divide and conquer it. We will first infer the ephemeral port number and then guess the transaction ID. So there are two problems to solve. Indicate the correct ephemeral port number and reduce the responsiveness of the name server. Let's now solve the first problem. In general, inferring open UDP ports is pretty easy. Just send a UDP probe packet with its destination port set to the port you want to probe. And if nothing happens, then you are right. The probe port is indeed open. Or if you receive an SMP reply, then unfortunately that port is closed as the operating system senses that no application is listening on that port. Ephemeral ports in UDP are like client ports on TCP, and they are usually only open to a specific remote host. Therefore, the direct port scan won't work in discovering ephemeral ports. In this figure, we can see even if the attacker's probing UDP hits the correct port number 1234, he still gets an SMP back, because that port is an ephemeral port, so it's open only to the name server and not open to the attacker. To deal with this problem, we can use IP spoofing, meaning we can send UDP probe packets by setting the source IP address to the same IP as of the name server. This does solicit SMP packets, but unfortunately, as shown in the figure, the SMP will be sent to the name server, and the attacker still cannot receive any feedback on whether the probe port is open or not. So, can we receive any other feedbacks when sending with the spoof IP address? The answer is yes, but not directly, and this is called the side channel. Anytime when there are shared resources, side channels can potentially arise, like the TCP side channel discovered by our group in 2016, where the TCP Challenge Act global rate limit counter is used as the shared resource between the attacker's connection and the victim's connection. This side channel uses SMP global rate limit counter as the shared resource. The counter limits the maximum amount of SMP that could be sent out during a period of time to mitigate the denial of service attacks. It's also shared by all remote IPs, including both the attacker's IP and the name server's IP. Specifically, in Linux, the counter has a maximum value of 50. Here is how we creatively exploit such a shared global counter for ephemeral port scan purposes. Initially, the resolver has 50 permits in its counter. To check open ports, the attacker sends 50 spoofed probe packets to 50 different ports. The resolver then generates SMPs for the probes. Based on whether the attacker hits the correct port, the resolver may reply with 50 or 49 packets, and the counter is deducted accordingly. Since no SMP is allowed to send if the counter hits 0, to reveal the status of the global counter, the attacker then sends a verification packet to close the port on the victim server, using his real IP address to try to solicit an SMP reply. If he gets the reply, meaning the counter is non-zero, and thus he found an open port. Otherwise, it means the counter has already hit 0, and thus no port is open. This side channel will give the attacker up to 1000 packets per second port scan rate when using the spoofed IP, and we have engineered our exploit carefully so that it could work even on poor networks with losses, delays, and jitters. Again, I would emphasize, without leveraging the global counter, we wouldn't be able to perform any kind of scan whatsoever. Since this is a design flaw of the operating system, it affects a large population of the machines on the internet, including 34% of open resolvers and 12 out of 14 public resolvers, according to our measurement. So till now, the port inference problem is solved. Let's talk about how to extend the attack window. As mentioned before, we only have hundreds of milliseconds to infer the ephemeral port number, which is usually the same as RTT between the resolver and the name server, and we call this the attack window. Even with our advanced scanning method, we still need 30 seconds to finish scanning all possible ports. So the larger the attack window is, the more ports we can scan, and the more chance we can succeed. Additionally, we can repeat the attack multiple times if we don't succeed initially, and as long as we finally succeeded, the cache will be poisoned for a long time, like a few days. To increase the attack window, we can simply flood the query traffic to overwhelm the name server. In fact, we found a bad name server can be easily overwhelmed by flooding random queries at less than 100k PPS. Furthermore, we also noticed at least 18% of name servers among Alexa top 100k sites deploy the response rate limiting. This allows us to easily mute those name servers at an even lower packet rate around 4k PPS. Since now we have already overcome the challenges, let's move on to the real-world attack. In this attack, our target is an open resolver in Tsinghua University, and of course, we get authorization to launch our attack on it. It serves the China educational network with 2 backend servers, and receives 70 million queries per day, which is a quite challenging target as it would bring background noise to the side channel. We also use a host on Tsinghua campus network as an attacker. But the link between the attacker and the resolver is not perfect and resembles a realistic attack scenario. We also set up our own domain with 2 name servers running bind on AWS in the US. And here is this screenshot showing a success attack where the A record of the victim domain has been modified to 1234 in the open resolver's cache. Overall, the attack works very well with a success rate of 100% or 5 out of 5, and an average time of 15 minutes to succeed. We also tested the attack with varying network conditions and server configurations to show the attack is robust in practice, but please refer to our paper for more details. What's more, with authorization, we also launched an attack against a commercial public DNS provider with 4 backend servers, serving an entire country. Surprisingly, we are able to successfully poison its cache in just a few minutes. Okay, now let's discuss the possible defenses. First, we can add more secrets to defeat the off-path attacker. Although these techniques have been standardized, in fact they are not widely deployed due to the backward compatibility and incentives. Second, we can remove the side channel to prevent effective port scanning. Now let's conclude today's talk. First, we introduced a novel side channel based on SMP global rate limit counter. Then, by using it, we revived the DNS cache poisoning attack. And finally, we showed our attack is powerful and can succeed on real-world resolvers in just minutes. Disclosures. We have already reported our vulnerabilities to the operating system community and related service providers. Besides, we have already worked with the kernel security team and the patches are on the way. Thank you.